in this course until now we have been discussing the homogeneous and isotropic universe, how it evolves, the thermal history, how we determine various parameters in this of the universe, etc. So, the key assumption, there are two of them, they are that the universe is homogeneous and isotropic. Now, if you look at the actual galaxy distribution around us, if this were actually really true, then you would expect the galaxies to be absolutely uniformly distributed. And if strictly speaking there would be no galaxies either, the matter would be absolutely uniformly distributed. But in reality you find that there is more matter in some places and less matter in some other places. So, you find galaxies. Galaxies are themselves demonstration that at the length scale of around tens of kiloparsecs, the universe is not homogeneous. The galaxy contains much more matter than outside the galaxy. Now, if you look at the distribution of galaxies, so you may then think that the galaxies themselves are uniformly distributed in space and moving away, expanding according to Hubble's law. But if you look at the distribution of galaxies, then the distribution of galaxies, this distribution itself shows clustering pattern. Okay. There are groups of galaxies containing few galaxies to around tens, 50 galaxy or so, and then there are clusters of galaxies. This picture over here shows you a cluster of galaxies called the Perseus cluster. Now, just look at this picture. In this picture, all of these fuzzy things that you see over here are actually galaxies. These are all galaxies. A cluster of galaxy is a part of space where you have a concentration of galaxies relative to the other parts. Just like a galaxy itself is a collection of stars, a cluster of galaxy is a collection of galaxies. So, this picture shows you a cluster of galaxies. This is a galaxy. There are many more galaxies here than you find in a typical part of the sky. Okay. This is called the Perseus cluster. This shows you the Coma cluster, and we have already discussed, we have already heard about the Coma cluster in this course when we were discussing the determination of the Hubble constant. Okay. So, this shows you a picture of the central part of the Coma cluster. The Coma cluster is one of the richest clusters of galaxies near us. Okay, it is actually the nearest rich galaxy, very rich galaxy. And except for this, this is a star in our own galaxy. Other than this, all the bright things, at least most of the bright things that you see over here are galaxies. These two are very bright elliptical galaxies. All of these that you can see are actually galaxies. Okay. So, this is the central region of the Coma cluster. So, a cluster, as you can now appreciate from these pictures, is a region where you have a dense collection of galaxies themselves with respect to the rest of space. I have told you that the mean separation between galaxies is around 0.1 per megaparsec cube, roughly of that order. It could be rarer also depending on the kind of galaxies you are looking at. Okay. But you see here in this picture that in the center of the galaxy or in the clusters of galaxies you have much higher density of galaxies in the cluster. So, this is a deviation from the homogeneity and isotropy on a larger scale. So, we have galaxies and we have clusters of galaxies. Clusters of galaxies are typically of sizes 1 to 10 megaparsec. You can make a formal definition. Abel, an astronomer called Abel, did pioneering work in identifying clusters and classifying groups of galaxies as clusters. So, he has given definitions of what he calls a cluster, and these are called Abel clusters, but we shall not go into that. For our purposes, clusters of galaxies are of size 1 to 10 megaparsec, and they can have up to 1,000 galaxies within this region. Okay. And these are typically small elliptical galaxies. You do not find many spiral galaxies in the clusters. So, these are old galaxies which have exhausted their fuel. So, there is not much star formation going on. So, you can see that there are many numerous small elliptical galaxies here. Okay. And there is practically no star formation going on. They have old stars, red stars. Okay. And there are a few big ellipticals also, and there could be up to 1,000 such galaxies in the cluster. Now, these galaxies in the cluster, if they would have collapsed in the gravitational potential of the cluster, there has to be something that prevents this collapse. So, these galaxies have random motions which prevent them from collapsing. Okay. And the whole thing is in equilibrium. So, the random motion balances the gravitational collapse. So, the kinetic energy of these galaxies, this is called virial equilibrium. So, these objects are the largest bound objects, and they are in virial equilibrium. The kinetic energy of these, so the kinetic energy per unit mass is V square by R, and the potential energy is G total mass by R. These are comparable, these are of the same order because these are bound objects in equilibrium. So, the kinetic energy and potential energy, the potential energy pulls it down. Okay. So, in virial equilibrium these are the same order. That is the kinetic energy, sorry, V square, there is no by R. That is the centrifugal. V square is of the order of Gm by R. The total mass, this is the total mass. This is the kinetic energy per unit mass of galaxy. Okay. So, the V square, this is the velocity dispersion, the mean V square, this is of the order of 1,000 kilometers per second. Random motions. And this straight away gives you an estimate of the mass of these clusters. So, Zwicky, famous astronomer, long before the rotation curve of galaxies were measured, the astronomer Zwicky had used this to come to the conclusion that there is dark matter. So, if you take this value and estimate the mass of the cluster, then you count the number of galaxies and estimate the mass of the cluster, it comes out to be much less. Okay. So, based on this, Zwicky had come to the conclusion that there must be matter which you cannot see in these clusters of galaxies. And the dark matter problem gets worse as you get to larger and larger scales. You need more dark matter as you get to large. So, galaxy, on the galaxy scale, I have told you that the rotation curve indicates the presence of dark matter. On cluster scales also there is indication that you need dark matter, and the problem gets more severe. Okay. So, this is the virial mass estimate. You can have other kinds of mass estimates also. Okay. So, these galaxies in the cluster, the way you think about them is that there is a potential well like this, that is the potential V, gravitational potential, it has a well like this, inside which these particles are moving around randomly. Okay. And these are balanced. So, there is a potential well of the cluster, the gravitational potential, inside which these galaxies are moving around. Okay. Now, the mass of these clusters of galaxies, if you estimate them correctly, say from the virial mass, or there are better mass estimates, they come out to be of the order of 10 to the power 15 solar masses. 10 to the power 15 solar masses. Okay. And in addition to, so this is a picture of the Centaurus cluster. You can see the galaxies in this cluster. This is a galaxy, this is a galaxy, this is a galaxy, these are all galaxies. This is the optical picture. Now, if you take an X-ray picture of this cluster, this is what it looks like. There is copious amount of X-ray coming out from this cluster. So, this is the X-ray picture of the same Centaurus cluster. Okay. And what is the source of this X-ray? So, there is hot gas with temperature 10 to the power 7 to 10 to the power 8 Kelvin, plasma. Okay, sitting in this potential well also. So, there is in this potential well there is plasma. It is filled with plasma. Okay, hot gas. And this has a temperature of 10 to the power 7, 10 to the power 8 Kelvin. So, it emits X-ray. It's the black body, the thermal radiation from this comes out in X-ray. Okay, such high temperatures. So, it emits copious amounts of X-ray, and the mass that you get for this gas is at least twice the stellar mass. So, the mass in the stars is not the dominant visible mass. The mass in the X-ray gas is the most dominant baryonic matter inside this. Okay, the mass that, so the mass of this gas that gives the X-ray emission is more than the mass of these, of the stars in these galaxies. Okay, but the dark matter is the most dominant component, and the 10 to the power 15 that I have told you is an estimate of the dark matter mass. So, if you assume that the X-ray is in thermal equilibrium, you know the temperature, you can actually work out the gravitational potential that you need to hold the X-ray in hydrostatic equilibrium. Straightforward exercise. There are also estimates based on gravitational lensing, which I shall not go into, which give you the mass. It is around 10 to the power 15 solar masses. Okay, but our aim here was not to study clusters themselves. This is, they are useful cosmological probe. My aim here to show you clusters of galaxies was to demonstrate, to give you some evidence that the universe on scales of megaparsec, tens of megaparsec, is not homogeneous and isotropic. There are structures called clusters of galaxies. So, you have concentrations of galaxies. So, you have concentrations of stars which form galaxies, then you have concentrations of galaxies. Some places you have more galaxies, there are groups, and then there are clusters of the size of 10 megaparsec. Okay. If you look at even larger scale, so this picture shows you the distribution of galaxies in a part of space. I have shown you these pictures earlier. Let me quickly show you. So, this is the picture that you get from the 2-degree field galaxy redshift survey, a redshift survey that was completed towards the end of the last millennium, 1990s, end of 1990s. Okay. So, this, each point here is a galaxy, and you can see how the galaxies are distributed in a region of space. So, the distance away here is measured through the redshift, and what is shown here is the angle on the sky. The angle, the other dimension is relatively smaller, so it has been compressed. Okay. So, this shows you the distribution of galaxies, and what you can see is that there are structures, there are patterns in the distribution of galaxies. It is not homogeneous. The number density falls off as you go further and further away. This is because you cannot see the faint galaxies over here. But in addition to that, you can make out structures over here. There are superclusters, galaxies are distributed in a network of filaments and which surround voids called the cosmic web. Okay. So, on scales of up to 100, possibly 70, 80 MPC, you have what is called the cosmic web. Okay. And you have a transition to homogeneity somewhere beyond the length scale of 70, 80 MPC to 100 MPC, somewhere over here. Okay. You have a transition to homogeneity, and beyond that scale it is more or less homogeneous at present. This is the Sloan Digital Sky Survey. Again, here it shows you the galaxy distribution in a part of space, very similar to the previous picture. Here again you can see that there are more galaxies in some regions and less galaxies in others. There is a clustering pattern. Okay. So, the question that we are going to discuss is the structure formation. How do these structures form in the universe? That is the essential question. There is evidence that the universe in the past was extremely homogeneous and isotropic. Okay. So, in the past it was and isotropic. One of the main evidences comes from the CMBR, cosmic microwave background radiation, which we have discussed to some extent, and this has fluctuations delta T by T of the order of 10 to the power minus 5. So, it is isotropic to a high degree. If the universe were not homogeneous and isotropic in the past, this isotropy would not be there in the microwave background radiation. This probes all the way to a redshift of 1000, right. We have discussed this. Last scattering surface is at a redshift of 1000, right. So, at that epoch, at least the universe was extremely homogeneous and isotropic of this to this order. At present, the universe is homogeneous and isotropic. It is homogeneous and isotropic on scales possibly larger than 100 MPC, somewhere over here. Okay. Now, on smaller scales, you see structures, which I just demonstrated to you, some of them. Question is, how do you start from a universe that is extremely homogeneous and isotropic and end up with a universe? So, we want to start with a universe that is largely homogeneous and isotropic and produce the present day observed universe. So, the initial thing is homogeneous plus isotropic nearly, okay. So, you have this as the initial thing and you want to produce the, this is at Z say of the order of 1000 and Z equal to 0, you want to produce galaxies, clusters of galaxies, the large scale structures that you see. These are called large scale structures, okay. So, large scale structures in the universe, LSS. You want to produce this. Question is, how do you get this? Okay. So, what is believed is that there were some initially small fluctuations that grow by the process of gravitational instability. To give rise to the present day structures that you see. So, there were some initially small fluctuations. We shall not go into the details of how these were produced. They were there. There are speculations as to what could be the mechanism to produce this in even earlier universe, earlier on. But for our purposes now, at redshift of 1000, 10,000, there were some small fluctuations, some very high redshift. There were small fluctuations and they grow by the process of gravitational instability to give the observed rise to the observed structures that you see. So, what is this gravitational instability? The basic idea is that you have a small fluctuation in the density, let us say. This is density and this is position. Okay. Some places you have more matter, some places you have less matter. Some fluctuation is there. The places where you have more matter will attract matter from elsewhere. Density is more, it will attract matter, and the places where there is less matter, the density matter will move out. Okay. So, whatever initial small fluctuation that you have provided gets amplified by this process called the gravitational instability. So, in the subsequent lectures, this is what we are going to discuss. Is it possible to produce the observed structures that you see by this means? So, if I had some initially small fluctuations, are these very small tiny fluctuations, are these fluctuations going to grow and give rise to the present day structures that you see? Is it possible? That is the question that we are going to address. Now, if you want to do a very rigorous exercise, then one has to do a fully relativistic exercise. Take the full Einstein's equation, put in your matter on the right hand side, curvature on the left hand side. You have the FRW metric, put perturbations and do a whole exercise. It's a little complicated, we shall not go into that. So, what we shall be doing is a heuristic Newtonian analysis. And this analysis, let me straight away tell you, it gives good results at low redshifts, matter dominated. When the perturbations are when the universe is matter dominated, and this is the first condition, which is I have told you somewhere around redshift of 10,000 we have estimated. Beyond that, so this is redshift z less than 10,000, quite a large redshift range. The universe is matter dominated. Okay. Second thing is that the length scale of the perturbation should be inside the horizon, much smaller than the horizon c eta. So, the length scale of the perturbation should be inside the horizon. If these two conditions are satisfied, and then the Newtonian analysis gives a reasonably good result. Okay. So, this is what we shall discuss to start with. Later on I shall briefly tell you what happens when the universe is radiation dominated, etc. Okay. So, how do we proceed? We shall treat the universe, the constituents of the universe, as being a fluid. This is a fluid. It is a self-gravitating fluid. So, the fluid exerts a gravitational force and the force acts upon the fluid itself. So, it is a self-gravitating fluid. Okay. So, something that flows. Okay. It is a continuous picture, continuum picture. Okay. So, we know that the universe is possibly made up of some kind of particles or galaxies or whatever, but on a sufficiently large scale we can think of it as some continuum, matter which is there, continuum. Okay. It has a density. So, that is the picture. Okay. So, this is the constituent. Let me just draw a picture. I am looking at a part of the universe in the Newtonian picture, and the constituent fills up this region. At every point there is a density. That is the continuum picture. There is a density, there is a velocity v. So, you have the density at every point, there is a velocity v, there is a pressure. So, each point will have a temp pressure. Two of these, pressure and density, can combine. So, two of these you can get the temperatures. If you know the pressure, you know the density. If you have the equation of state, you can get the temperature. So, you do not need to give this separately. Okay. And you have then the internal energy, but we shall not be dealing with the energy equation. Once you know the temperature, you can also calculate the internal energy, the energy of the thing, and look at the conservation of energy, but we do not need that here. Okay. So, so for our purposes, these are all that you will need. The fluid has got a density at every point. It is a fluid, it is a continuum thing, and there is a unique velocity at every point. It is a continuum, and there is a whole fluid at every point has a velocity. Let me call the velocity u. Okay. At every point there is a velocity u, and the fluid at every point, it is some medium, so it has a pressure also. Okay. It is a continuum description of the whole fluid. We would like to determine, first work out the equations that govern this. Okay. So, the first equation is the conservation of matter or mass. Mass conservation. So, let us take a region V which is immersed in this fluid. So, the mass inside this M is the volume integral of rho d tau. Tau is the volume over the volume V, that is the mass. Now, I ask the question, what is the rate of change of mass? So, this we can calculate, the volume is fixed. So, this is going to be del rho del t into d tau, that is the only way that mass can change, integrated over the same volume V. And we know that mass is conserved. So, if the mass inside changes, it must be due to a flow of mass. So, if the mass inside changes, this can only occur if the mass is either flowing in or flowing out. So, the mass has to flow, otherwise the mass inside cannot change. Mass is conserved, we know that. So, what is the, how much is this the flow of mass? And the flow of mass is going to be the mass current. The mass current at any point here is rho into V, that is the rate at which the mass is flowing, rho into V, into the surface area dA, where dA is oriented outside, outwards. So, this is dA on the surface. This surface integral will give me the rate at which mass is flowing out with the, so this will be minus dm dt. If this term is positive, then the mass is flowing out, dm dt is going to be negative. Okay, so this is the mass current, rho into V, dot dA gives me the mass flux. Okay. So, we know that from the conservation of mass that dm dt should be equal to this, and it is also equal to this from the conservation of mass. Okay. Now, this integral we can convert using Gauss theorem to a volume integral over the volume V, and there will be a minus sign, and the integral is of the divergence of rho V. So, that is the Gauss theorem d tau. So, now I can just equate these two, because this is the rate of change of mass, it has to be equal to the flux, mass flux. So, what this tells me is that del rho del T plus the divergence of the mass current, this is should be equal to 0. This is the continuity equation. And what it tells us is that the mass is locally conserved. I do not create or destroy mass. So, if the mass inside a volume goes down, it must have flown out. If it goes up, it must have flown in. Okay, so, this is the mass current. So, the del rho del T, the rate of change of density, is the divergence plus the divergence of the mass current should be equal to 0. Okay, so, this is the continuity equation, the mass continuity equation, it comes from the conservation of mass. Second, we have the conservation of momentum. So, momentum conservation. Again, let us take a volume over here, and let us ask the question, what is the x component of the momentum inside this? Px, total x component of the momentum. I am dealing with just the x component. This is going to be, so the x component of the momentum inside this volume V is going to be rho into Vx into d tau integrated over the volume. Rho into Vx is the momentum per unit volume, mass into velocity, and integrate over d tau will give me the total momentum. Now, we want to calculate how much is the rate of change of momentum inside this volume. Exactly the same thing. So, this can in principle change, because this can be written as del by del T of rho into Vx d tau, right. If rho into Vx changes, the whole thing, so the time derivative is of the product rho into Vx. If this changes, then the momentum will change. Okay. Now, again this will be the momentum flux. Momentum has to either flow in or flow out, that is one possibility. So, this will be equal to minus the momentum current is rho Vx, that is the momentum. I multiply this by V, that gives me the current, dot dA, exactly the same thing. You see, when I wanted the current for density, I multiplied density with V. So now I want the current for the x component of the momentum. So I multiply rho Vx x component density for the x component of momentum into V. That gives me this is the momentum current for the x component of the momentum. I hope it is clear. This dot dA gives me the flux. Now, in addition to this is the momentum that flows out. In addition to this, I can have inside a fluid, we know that there is pressure, and pressure we know. So if this is the surface, we are dealing with the surface dA. This is the surface integral over the surface S. If this is the surface, for a Pascalian fluid, we know fluid that follows Pascal's law, the pressure is going to be normal to the surface, and it will act inwards, opposite, right. So this is going to exert a force, and this force is going to be minus, let me put this force here. So this is going to be minus this integral, again the surface integral, and so we are interested only in the x component of the force. So I have to take the x component of the surface area, right. So what I have to write is the pressure into the x component of the surface area, which is the unit vector along the x direction, dot dA. That is the force due to the pressure. Now, if it is a, okay, now the next thing is we are interested in a self-gravitating fluid. Now, a gravitational field can be expressed in terms of a potential, we all know this, and the force that is going to act per unit on any unit element. So this is a unit element of the fluid. So this unit element has got volume d tau. So the force that is going to act on this can be for a gravitational fluid, a fluid in the gravitational field, any fluid in the gravitational field can be expressed as minus grad phi, gradient of a potential. Phi is the gravitational potential. This into the mass into acceleration, this gives me the acceleration. So this into rho, the integral of this over the volume, is the other force that acts on it. So I have the flux flowing out, the momentum flowing out. In addition, the momentum can change due to forces. There is this force due to pressure, and there is this force due to the gravitational field. Okay, this is the acceleration, this is the mass per unit volume. So d tau I integrate over the whole thing, that gives me the force, and I should take only the x component of this. I am interested only in the x component of momentum. Okay, so this is the equation which governs the rate of change of the x component of the momentum. Now what we have to do is do exactly the same thing that we had done earlier, convert this and this to volume integrals, and then we can straight away equate the left hand right hand side, we will get an equation. So let me write it down. So what we get from this, let me first convert this into a volume integral. So when I convert this, so let me write down the equation. What I have is the volume integral del by del t of rho Vx d tau. This is equal to, I convert this into a volume integral. So what I have is that this will be equal to minus the volume integral del divergence of rho Vx into V d tau, right. So this divergence is actually the index over here. When I take the x component, this should be x, y component, this should be y, z component, this should be z. Okay, and then I have another term which is minus, let me put that term here. I have to take this and use Gauss theorem. So what I will get is minus divergence of P into I. This is a vector which has only x component, dot d tau, and I have the term which was already there, which is minus grad phi rho d tau. Now when I take this divergence, I will only have the x derivative, because this vector has only x component, right. Here I will have all the components. So now I can equate these, the left hand side, right hand side, and the equation that I get is that del t, the time partial derivative of rho v x is equal to minus this term becomes minus del by del x of P, because this vector has got only x component. So when I take divergence, there will only be del by del x of this, del by del y acts on 0, del by del z acts on 0. This vector has only x component. This vector has only x component. I want only the x component of the surface area. This minus rho into, again here I should take only the x component, which I should have written here earlier, because we are looking at only the x component of the momentum. I have written it here. So this will be minus rho into del by del x of phi. That's the equation. Now we can simplify the left hand side a little bit. So the left hand side, let me just write down this term. The left hand side, if I write it out, it becomes, let me write out the left hand side. It becomes, there will be two terms. One term is Vx del rho del t plus rho del Vx del t, that is this term here. Let me write out this term also. This term, there will be two terms here. One term is going to be, I can take the Vx outside, so this is going to be minus Vx into divergence of rho v, that is one term, and the other term is going to be minus rho v dot gradient acting on Vx. So this term I have written here. Now you compare this left hand side and right hand side, you will see that del rho del t, this term and this term, the terms of, if you take Vx common, you get the continuity equation. You take Vx common and what you have is this, del rho del t is equal to minus divergence of rho into V, which is what you have here. Del rho del t is equal to minus this. So these two terms cancel out, and what you are left with is this term, this term, this term, this term. Okay. So let me write it out here. What you are left with is rho del Vx del t is equal to minus V dot grad Vx minus rho del P del minus del P del x minus rho del phi del x, right. So I have just taken this equation, written this term, and these two remain as they are. So that's what I get. Now this is the conservation of the x component of momentum. I will have similar equations for conservation of y component of momentum and z components of momentum. I can combine all these three, and finally what I will get is rho del v del t plus, I can take it onto the right hand side, v dot grad v. So this is acting on this is equal to minus grad P minus rho grad phi. And I can divide throughout by rho. Oh, there should be a factor of rho here also. There will be a factor of rho here also. I can divide throughout by rho, and what I have finally is del V del T plus V dot grad acting on V is equal to minus 1 by rho grad P minus grad phi. This phi is the gravitational potential, this P is the pressure. Okay, this is called the Euler equation, and it is the conservation of momentum. There is a third equation that we need. The third equation tells us what the gravitational potential is. So, the third equation is as follows. We get this as follows. Consider a mass distribution over here, okay, and the mass, we are interested in calculating the gravitational potential at this point r. The point r could be inside this mass distribution. I have just drawn it here for pictorial representation. This mass distribution is rho x, rho r, let us say. So, rho r prime. Okay. So, question is, what is going to be the gravitational potential here? And the way you calculate it is to use the superposition principle. You take a small element at a distance rho prime, r prime, so what is the potential at this point due to this mass here? And we know that this phi r is minus g into the mass over here. The mass over there is going to be rho r prime d tau prime, that is the mass in this volume, divided by the distance minus gm by r, and the distance is r minus r prime. So, we have to integrate this over the whole of volume, and that will give me the gravitational potential at this point, right? Superposition principle. The gravitational potential is minus gm by r, where r is actually the distance between these 2 points. So, the gravitational potential produced by this mass element is minus g into the mass divided by this distance. I have to add up the contribution from all the mass elements. So, this is what I have. Okay, you can also think of this in terms of the Green's function, etc., but we do not require all that. Now, it is more convenient to write this equation in the form of a differential equation, del square phi r. Okay, and we know that del square of 1 by r is minus 4 pi times the Dirac delta function, 3-dimensional Dirac delta function, delta x, delta r. Okay, this is known. I shall not go into the proof of this. Del square of 1 by r is minus 4 pi into the 3-dimensional Dirac delta function. Okay. So, when you take del square of this, you will get basically the 3-dimensional Dirac delta function when r and r prime are same. Okay. And if you, this minus sign is gone because of this. So, when you now do the integral, what you get is that this is going to be equal to 4 pi g rho r. This is called the Poisson equation. It has exactly the same information content as Newton's law of gravity. Right, the gravitational potential is a Newtonian gravitational potential. The minus gradient of this will give me the gravitational attraction, acceleration. Okay. So, this is the Poisson equation. It expresses the Newton's law in a differential form. So finally we have these three fluid equations that we are going to deal with, and there is nothing very specific to cosmology about this. These are the general fluid equations. That we are going to use to describe this medium that fills the universe in which we are going to put perturbations. Okay, we are going to put small disturbances and see how they grow. So these equations are the continuity equation del rho del t plus the divergence of rho v is equal to 0. That is the mass continuity equation. The second equation is the momentum conservation equation. This is the continuity equation del v del t plus v dot grad acting on v is equal to minus grad p by rho. If you know the, so you have the density, you have the velocity, the pressure, if you know, okay, so pressure is also there, you need to know the pressure, and minus grad phi, okay, and we have del square phi is equal to 4 pi g rho. So this is the Euler equation, the momentum conservation, and this, the third one, is the Poisson equation, the law of gravity. So very quickly we have gone through the derivation of the equations that govern the evolution of a fluid, and we are going to treat our whole universe as being made up of a fluid. Okay. The basic approach is that is going to be a perturbative approach. So we have a homogeneous and isotropic universe, and in this homogeneous and isotropic universe we are going to put in a small perturbation, and we are going to see how this perturbation grows, evolves. Does the perturbation grow? If it grows, then you can in principle produce the observed structures that you see by the growth of perturbations. If the perturbations do not grow, then it is out of question, or if they do not grow sufficiently, then again it is out of question. Okay. So this is the these are the equations that we are going to use to study large scale structure formation. Now so the first thing, so these are the fluid equations. The first thing that we are going to do, let me do one simple exercise first. Let us first forget about the expansion of the universe. So no expansion. Okay, as the first step, let us forget about the expansion, no expansion. So we have this universe which is homogeneous and isotropic. Okay. So let us consider a static universe. Density rho is a constant. In principle it could be a function of r and t. We will assume it is a constant, rho bar. So there is matter uniformly distributed everywhere, it has no velocity. So we will use u for velocity, okay. So u is 0, I am just changing notation to u, we have been using v throughout. U is 0, and the pressure, you see in this equation what contributes is the pressure gradient. The pressure we will assume also to be, pressure will be related to density through some equation of state. So pressure also we will assume to be constant. and the gravitational potential. So, this is a static universe, it is infinite, and the matter is uniformly distributed. So, there will be no gravitational attraction in this acting, trying to pull the matter from one place to another. So, we will assume that phi is 0. That is the initial condition. So, we have a universe homogeneous and isotropic. Okay. So, we have a uniform matter distribution, that is the basic picture we have. So, we have a uniform static matter distribution. Okay. Now, in this we put in a small perturbation, disturbance. So, we have this uniform, no expansion, and it is a uniform matter distribution. Okay. In this we put in a small perturbation delta rho. So, if you perturb the matter, you can also produce velocities. So, there will be a small velocity v, there will be a small pressure also, different pressure some in different places, delta p, and there will be some potential also, let us call that psi. Okay. And all of these so these are all perturbations. So, delta rho is a change in that. So, I have this uniform density on which I have put in a small change somewhere it is. So, this is a function of r and t, it is not a constant. Similarly, this v is a function of r and t. So, we will assume that these are all small numbers of order epsilon. So, we have put in a small perturbation, small disturbance, and this epsilon is a small number that quantifies the fact that they are small. Okay, it is an infinitesimal epsilon. So, we have put in a small density fluctuation, a small velocity fluctuation, small pressure density fluctuation will cause a pressure fluctuation. Okay, and then this if I have matter more somewhere, less somewhere, it will cause a gravitational the fluctuation in the gravitational acceleration also. So, we have introduced these fluctuations and these are assumed to be small of the order of a small number epsilon. Okay. So, how do we proceed now? What we are going to do is called perturbation theory. So, this is what is called perturbation, linear perturbation theory. Okay, we are doing perturbation theory and we shall only work to linear order. So, let me take up the continuity equation first. This is the continuity equation. In this continuity equation, the density is the uniform part which is constant plus a fluctuation. So, when I write down the continuity equation, I am going to only have a time derivative of the fluctuation. Now, when I take the divergence of rho into v, rho into u, I am assuming using u here for the velocity, rho into u. So, there will be one term which is just rho into the small velocity fluctuation that you have introduced, and there will be another term which is delta rho into v. Now, the term delta rho into v, so there will be one term, let me write it down, the partial derivative of delta rho with respect to t is the first term. Then let me write it down, I will have, there will be two terms, 0 plus delta rho, sorry, rho bar plus delta rho, and then I will have 0 plus v. This is my equation. Now, we are going to work to only first order in this small parameter epsilon. Now, notice that the term delta rho into v is of the order of epsilon square, and epsilon is a very small number. So, this is much smaller than epsilon. and we will ignore all terms of order epsilon square. So, this equation then becomes so the only term that survives is this rho bar into V, and rho bar is a constant, so I can take it outside. So, this equation now becomes this, where V is a small perturbation to the velocity u. So, what is the, let me just go back to the basic fluid equations. The fluid equations are non-linear. Why do we call these non-linear? Well, there is a product of rho into V. Here again there is a product of two V's. Okay, so this makes it non-linear. Here I have P by rho. Okay, so this makes it non-linear, and solving such non-linear equations is very complicated. You do not have analytic solutions by and large, general analytic solutions. Solving linear equation is very simple, but non-linear equations are difficult. So, what we have done, what we are going to do is we are going to assume that there is some background solution on which we are putting in a small disturbance, and then we can linearize with respect to this disturbance, and we shall get some linear equations which we can solve. So, we have done this for the continuity equation. In the next class I shall discuss how this can be done for the Euler equation also, and then we shall discuss the solutions. Let me stop here for today.